And so we're back, and we're talking about energy as it pertains to work. And I think I mentioned one or two videos back that work and energy are very closely related. In fact, that's why this chapter is called Work and Energy, because they can be thought of as kind of the same thing. So here's a way that we're going to take what we know already, and we've got right here a kinematics equation that I hope you recognize. And we're going to combine it with what we know about force and acceleration, and we're going to derive an equation that tells us how work is related to mass and velocity. Okay, mass and velocity, these can be stated as energy. And you probably, in fact, I'm sure you've heard of kinetic energy before. That's oftentimes, didn't want to do that. It's oftentimes referred to as the energy of motion. And in order to have motion, we need some sort of velocity. So these velocities, initial velocity and there's our final velocity right there, are going to be very important in the deriving of the equation to determine how work is related to mass and velocity. Well, if you recall, Newton's second law is F net equals mass times acceleration. And if you recall, up here our equation looks slightly different. And by the way, I'm doing these in a little bit different order. This is our equation where we wrote it as V final squared equals V initial squared plus 2 times acceleration times our delta x displacement. Well, we've taken to using d to describe our displacement. It's really distance, not so much as a displacement, but everything else looks almost the same, with the exception of there's no f in the first v right here. It's just assumed that velocity at any point in time is the final velocity as opposed to the initial velocity. So this equation shouldn't be too different from what you're used to seeing. Okay, well let's state this. Let's state our velocity and acceleration and displacement equation in terms of acceleration. Okay, so acceleration, 2 times acceleration times, we're going to say d instead of delta x, but you should know that they're essentially the same thing, equals vf squared minus vi squared. Okay, and since Newton 2 tells us that the net force is equal to mass times acceleration, then we can state that acceleration should be equal to net force divided by our mass m. And you can probably figure out what the next step is here. We're going to be substituting. We're going to be taking our acceleration and dropping it into our equation for velocity and acceleration and displacement. And so we're going to have what looks like this. And I'm going to, I don't want to do that. Go all the way up top here. Okay. That means it's going to be 2 times net force over m times our displacement equals vf squared minus v minus vi squared. Okay, we just combine these two equations right here. Both of these we know from before, but we're going to come up with an equation that speaks about work in terms of velocity and mass. All right, well, let's simplify this a little bit. Let's take our m, actually, and our 2 right here. If we bring them across to the other side, the m is going to come up top. Okay, right, and our 2 is going to come down to the bottom right there. So really, we're going to be left with this: f net times our distance equals m on top, m vf squared over 2 minus m vi squared over 2, right? And by the way, if you're wondering how I did that, I took this 2 and this m and distributed it. And by the way, I kind of skipped a step here. It's like saying this: F net times D equals m over 2, right? Because we actually brought the 2 down and the m up, times Vf squared minus Vi squared. Okay, then I distributed the m over 2, and we have our equation as it sits right now. Okay, we'll take a look at this then. F net times D, well, we know that by this point to be work. Our net work equals all this over here. And the notation for this is more like, instead of the 2 on the bottom, we take the 2 and put it out front as a 1/2. So it's really 1/2 mv final squared minus 1/2 times mv, better v than that, mv initial squared. Okay. And I just lost my place here. Oh, okay, I'm at the bottom of this, actually this next slide. In fact, you know what? I'm going to move this layer around. There we go. This is the next slide right here, and I just overlaid it over top of the previous slide. But these are the steps that we just did right now. We substituted F net over m for a, and we took the 2 and the m and we distributed it to the other side, and we have an equation that looks like this right here. Net work on an object is 1/2 mv final squared minus 1/2 mv initial squared. And that's what we have right here down at the bottom of that page. The 1/2 mv squared is an equation for what we call kinetic energy. There we go. That's this right here. Kinetic energy is defined as 1/2 mv squared. And you can see how it's very closely related to work. If work net equals 1/2 mv final squared minus 1/2 mv initial squared, if both of these are the definition for kinetic energy, we really say that the net work done is the final energy, final kinetic energy minus the initial kinetic energy. Kinetic energy is a scalar. It's simply measured in one direction. It's determined by the speed or the velocity v. Okay, the faster the higher the velocity, the greater the energy is going to be, and it has the same units that work has. It's in joules. By the way, if our initial velocity is 0 right here, if vi equals 0, then what does that do to the second part right here? What makes that whole second part equal to 0? So it's really saying that the net work done is 1/2 times the mass times the velocity, or the final velocity, squared. So it makes sense that they should have the same units as work. That unit is joules. And if you look at all of our units, if we were to write all of our units out, mass being in kilograms, velocity being in meters per second, and then square that, it would be meters squared per second squared. That means that 1 joule is 1 kilogram meter per second squared. Sorry, 1 kilogram meter squared per second squared. I think we're all glad that it's just simply called a joule. But that's the unit for work. That's the unit for work. So let's expand this a little bit. If we know this to be true, if we know the net work is the final kinetic energy minus the initial kinetic energy, Well, then it's the change in kinetic energy. Net work can be described as simply delta K. Now, that looks overly simplified, and it certainly helps to know that K consists of 1/2 mv squared, and it consists of that because of what we just proved by deriving that last formula. But we call this the work kinetic energy theorem, and you're going to find it to be very, very helpful. I'm going to give this. I'm going to wrap this video up and save the next and hopefully the last video for our examples. It's going to be example 8.5 and 8.6. So I'll see you on that.